Yeah, I think we're all set, so go ahead and do your talk. Andrea is going to talk to us today about Stochastic MiniZinc. Thank you.
Thanks, Nick. So hello, everyone. I'm really happy that I can present the current work, an extension of MiniZinc. This is joint work together with Guido Tack and Peter Stuckey. And before I get started on how we extended MiniZinc to allow implementing stochastic problems, I'm going to cover all the background. So I'll start with an overview of MiniZinc, what is the current state. Then I'm going to continue with some background on stochastic optimization, what are the basic concepts, and I'm going to assume that you guys have no detailed knowledge of stochastic optimization. So sorry if you already have an idea about that. Then I'm going to continue showing you the actual language, stochastic MiniZinc, and then the transformations and some conclusions. I tried to include as many images as possible in this talk, and so there are no formulas or anything, so I hope you guys can follow me. So the basic idea of MiniZinc is that we have this kind of model and solve approach. So we have MiniZinc on the higher level, it's a high-level modeling language, and we can transform this language into so-called FlatZinc. So FlatZinc is a low-level language, and if you would compare it, for instance, to programming languages, you would say that MiniZinc would be something like a high-level programming language like Java or like C++, and FlatZinc would be some kind of assembly languages. On bottom of that, we have solvers who can solve FlatZinc, who can interpret FlatZinc, and the nice thing about this whole translation is that we can translate a model to different solving paradigms. So we have constraint programming, we have mixed integer programming, we have SMT, and we even have SAT very soon. So Ignacy here in Melbourne, he is currently implementing a SAT translation as well. So what this means is that this model has to be transformed to these different paradigms, and I'm going to show you an example on how this is going to work. So first, an example of the n-queens problem in MiniZinc. The n-queens problem is very well known. The objective is to place n queens on an n times n chessboard. So what we have here first is we include the globals library, which includes global constraints. As you can see, we're using the global constraint all different here. We're defining a parameter n. We have a variable array that ranges from 1 till n, and that we name queens. And we specify constraints, which is basically we represent the problem in such a way that we say the queens variable represents in which we have a variable for each row in the chessboard, and the value for each variable, each row tells us in which column we place the queen. So we first say all different over the variables, which means that no queen may be in the same column, and two all different constraints for the diagonals. After the constraints, we specify the search and the objective. So we specify here that we want to have an integer search over the queens variable as search variables, the first fail strategy, smallest domain first, and a complete search. And with satisfy, we specify that we only want to have one solution, so we have a satisfaction problem, and if you would have an objective, an optimization problem, we would specify the objective here. Finally, we can specify the output, and here we basically say that we are actually printing the chessboard with this using a comprehension. So we have I and j that range over 1 till n. And if queens at position I is fixed to j, so if it's assigned the value j, then we print q, and otherwise we just print a dot. And in addition to this model file, we also give a data file where we specify, for instance, that n equals 8. So this is a very basic idea of how MiniZinc works. Now, how does MiniZinc look like in FlatZinc? So if we translated MiniZinc to CP-style FlatZinc, what we would see is we would have variables that are representing for the array variables, and we have auxiliary variables that are here representing intermediate steps. And you can see we can use the all different constraint in the constraint solver, and other constraints are translated to linear equalities. So for illustration, how would the same problem look like for a linear solver? Here we can see the FlatZinc for a MIP solver. As you can see, we first have, again, those variables just as, so we can later on reproduce the output. And then we have 0, 1 variables, basically up to 496 of those to represent the problem. And all the constraints are transformed into linear inequalities and equalities. So finally, after solving this problem, we get this as an output as we have specified in our problem. So you can see the queues mark the places where each queen has been placed. So the very nice thing now is that we even have an IDE for MiniZinc, thanks to Guido, who has implemented this in this year. So this is illustrating the IDE. I hope you can see it properly. So it's really a very nice editor with syntax highlighting. You can also you can open your model file. Here you have your data file, and you can see the output just below. The nice thing is also that you can configure your solver. So here you can actually select the solver with which you want to solve the problem. And you have a nice project explorer and so on. So I highly encourage you to check out the MiniZinc IDE. Okay, so far to MiniZinc. Now let's move on to stochastic optimization. So the principle about stochastic optimization is that in our world we see a lot of uncertainty. So uncertainty can arise in most of our optimization problems, but what we usually do is that we ignore it. But what we would want to do is we would want to include uncertainty into our problems. So uncertainty can cover travel times, it can be about demands, it can be about capacity, and so on. So what we do in stochastic optimization is that we consider a problem where some parameters are uncertain. So as I said, this can be the demand, the travel times, capacity, and so on, but they're not just uncertain, we can also estimate them. So usually what we would have some historical data, or we would just use a probability function to approximate the actual data. So one important notion is that of problem stages. So if we consider time here in this graph, at some point the parameters become known. So there's a stochastic event, and the stages basically tell us when the parameters are going to be known. So in the first stage, the parameters are not going to be known, but in the second stage, the parameters of the first stochastic event are going to be known. So I'm going to show you an example of two-stage problems. Those are the most common problems, or they're also the simplest versions of stochastic optimization problems, where we have to make first-stage decision before we actually know a stochastic parameter. So we have first-stage decisions, then a parameter becomes known, and then we have second-stage decisions, which are also called recourse decisions. And it's really important to understand here that the thing that we really want to know are actually the first-stage decisions. We want to know what to do before an event, a stochastic event, occurs. And the second-stage parts are really just parts that deal with decisions that we have made and with consequences of this outcome of the parameter. So as an example, let's consider we have to decide the production at a car factory. So in a car factory, producing a new set of cars takes quite a long time, and we have to start with the production before we actually know the demand. So we have to decide how many cars to produce before we know the demand. So these would be our first stage decisions. Then after we actually know the demand, we can make recourse decisions that depend on if we have an overproduction or an underproduction. So the recourse really is dealing with how many costs would come up if we have an over or an underproduction. So to solve those problems, what we introduce is the notion of a scenario. So scenarios are possible outcomes of stochastic parameters. So for instance, the demand. And for each scenario, we assign a weight, which is often the probability. And what we consider in this context is only that we have a finite number of scenarios, because otherwise the problem is not solvable. So for this example of the car factory, here I illustrated the case of 3 scenarios. We have a scenario where we have a high demand, where we have a medium demand, and where we have a low demand. And those red blobs show us the actual probability of each. So we have to decide how many cars to produce, and we estimate that the demand can have 3 different outcomes. So with a 20% probability, it's going to be high demand, with 50% a medium demand, and with 30% a low demand. So what is the overall objective? The objective is to minimize or to maximize the expected costs. So this means that if we consider n scenarios, the objective is exists of the first stage cost plus the expected second stage cost. So we have a sum over all the costs over each scenario weighted by its probability and divided by the number of scenarios. So what about solving approaches to these kind of problems? If you have a linear problem and if you have continuous variables, then you're on the safe side. So there are many different solving approaches that are also quite effective. So the bad news is that as soon as you have nonlinear constraints, or if you have integer variables, then things get really messy, because you no longer have certain properties that you would have in the linear and continuous case. So this is bad news for us, because we're working on combinatorial problems, and so far there are only 3 known approaches for solving this, and they're not even very effective, but at least most of them are not very effective. And still, all of those approaches transform this stochastic formulation into a deterministic equivalent. And I'm not going to talk about these approaches now, but later on, because we're going to see how we can transform this stochastic formalism into those deterministic problems later in the talk. Okay, so now you know everything about stochastic optimization, and we can move on to stochastic MiniZinc. So first of all, what were our objectives in designing the language? The main objective was, first of all, that we want to have a conservative extension. So this means that a model that you specify in a stochastic way should also be solved in a deterministic fashion as well. The second objective is that we want to allow the user to have a formulation that is agnostic of the solver technique. So this means that if you, as a user, want to formulate your stochastic problem, you don't have to commit to a certain solving approach. But this is what you have to do nowadays. If you want to use one of those 3 solving approaches that I've been talking about, you already have to commit to them when you formulate your problem. The third objective is that if you want to specify your model, you should have only just a little background on stochastic optimization should actually suffice for you. So this means that you don't even have to know about those solving approaches, and you don't have to know about how do you have to formulate your problem in order to solve them in such a way. And fourth, this extension should be lightweight and therefore not much work for us in the end. So what does the problem formulation consist of? A stochastic specification consists of, first of all, the problem model that contains stochastic annotations, and second, with the deterministic data specification. So these are data that are known, that are not uncertain, and then stochastic data that specifies your scenarios and the probabilities. So the kind of annotations that we have introduced are only 3. So the first one is an annotation to label which stage each variable belongs to, or each parameter. Then we have the annotation expected, which you can use to annotate that you would like to minimize over the expected cost. And finally, an annotation to specify which are the scenario weights for your scenarios. So let's have a look at a nice example for this. The vehicle routing problem, which most of you will know. So what you can see here is a graph. We have a depot and a number of vehicles and a number of customers. So in this graph, the round circles represent customers, and we have a time budget, we have service times per customer and a distance matrix, which are all omitted now in this graph. So you have to imagine that traveling from one node to another costs a certain amount, and at each node we have a service time. So what is the objective of the vehicle routing problem? The objective is that we want to assign each customer to a vehicle, and we want to have optimal tours for each of the vehicles. And our objective is to minimize the travel time. So here you can see a solution for the red and the green and the blue car. And now the question is, what is the stochastic factor in the VRP? So the stochastic factor is often the travel times, because if you look into reality, travel times are never certain. They're often uncertain. So what I've tried to depict here is that you will often have congestions over certain paths, or certain paths might be actually traveled, you can travel them much quicker than you would expect it. So here you can see along this line there is a big congestion, and here you can actually travel quite quickly. So this could be one scenario. Maybe you know from historical data that these are the routes that are often congested, but you might also know that sometimes there are actually some other routes that are quite congested, and other routes that are very easy to traverse. So what you might want to know is how can I do the stochastic formulation that we consider here is that we consider the travel times are uncertain, and as a first stage decision we want to assign each customer to a vehicle. And in a second stage decision, we want to have a tour for each of the vehicles. And overall, we want to minimize the expected travel times. So what this means is that we actually really just want to know this vehicle customer assignment. This would be, for instance, make sense if, let's say, we are a company who is servicing customers with key services, for instance, and before each vehicle starts on its tour, it needs to have the equipment that is necessary for each customer. So they have to know in advance who they're actually going to visit. So we have to know in advance, before we know the travel times, we have to know which vehicle is going to visit which customer. So this is actually quite difficult, because this means that for each vehicle customer assignment, we have to solve a TSP in the recourse in the second stage. So this is really demanding. So just for illustration, the first stage decisions would simply assign customers to each vehicle, and in the second stage, the recourse would be a tour for this assignment. So he would have, for instance, tours for scenario 1, and he would have a recourse for scenario 2, just because we know that the travel times are going to be different in each scenario. So how can we model this problem in MiniZinc? Here is an excerpt of the problem. So the additions that we have are all in red. So you can see it's a really lightweight extension. So we have here some parameters like the service time, and we have here the distance matrix. So the distance matrix is our stochastic parameter, and this is why we annotated with stage 2. Then we come to the variables. The vehicle customer assignment is, as we said, a first stage decision, so we label it with stage 1. And all the other variables, like the successor and arrival time variables, which correspond to the actual tour, are second stage variables. So we annotate them with stage 2. If you do not annotate something like service time, this means automatically that it's a stage 1 problem, a stage 1 parameter, or stage 1 variable. And if we continue to the constraints, you don't have to annotate anything. And finally, in your objective, you annotate that you would like to have the expected costs of the travel times. So this is the first part, the problem model. Now we come to the second part, which is the stochastic data specification. So there are two ways to specify the stochastic data. The first way is to give each scenario in a way like as a historical data. So you would give several files. So you have here the first distance matrix for scenario 1, the second distance matrix for scenario 2, and here you have a specification file that tells you the paths to the scenario files and gives the weights as well for each of them. So in this case, both of those scenarios have the same weight. Now, the other way of specifying the stochastic data is by giving the the scenarios in one big array. So here we have the first scenario and the second scenario, and the weights given annotated with scenario weights. So either you can give this specification, or you can give this specification, which will automatically generate the other specification in the tool. And of course, the third part of the specification is to give the deterministic data, like the service times, the number of vehicles, and so on. Okay, so this is the stochastic VRP. So now you've seen how easy it is to model your problem. You really just have to annotate to which stage each variable or parameter belongs, and specify your scenarios. You don't need to commit to any solving approach. So now let's move on to the transformations. Why do we need transformations? First of all, because we want to use this whole tool chain again that you've seen before. So we're translating from stochastic MiniZinc to deterministic MiniZinc. And how are we going to do that? So basically there are two parts. There's the model transformation, and we also have to specify specific searches, which we do by the use of search combinators. And as I said before, we have transformations to all three different solving approaches. So before going to the details of the transformation, I want to give a bit of background on search combinators themselves. So search combinators are a kind of language for specifying search, and they're compositional, which means that you can combine search combinators in any way. And I'm going to give you some examples. So what you have is basically you have a set of primitives, and those primitives can be composed as much as you want. Here is a little list of them. So prune, for instance, just prunes the current search. Base search is a primitive to specify a basic search. So you give some variables, you give a variable selection heuristic and a domain split heuristic. Assign assigns to the variable an expression. Let defines a local variable. So it defines variable var, initializes it with expression within the scope of search. Then we have post, and posts the constraint CT in the scope of this search. And we have other combinators like and search. So this basically says search 1, search 2, and so on. And similarly, we would have or search, restart search, and so on. And as an example of how you can compose those search combinators, here are two examples. So how would you specify a search combinator to search just exactly for one solution? So let's call this combinator once. So once, given a search strategy S, says if condition solution smaller than 1 holds, then perform search, otherwise prune. So this is really simple. Let's have a look at a bit more advanced one, which is a CP branch and bound search combinator. So we call the search combinator branch and bound, given an objective variable and a search. We define the variable best that we initialize with infinity. So we are minimizing here, by the way, and in the following scope. So we post that objective has to be smaller than best and perform an and search on this array. So we perform search, and then we assign to best the objective. So yeah. So this is the branch and bound search combinator, and we've used search combinators to specify those specific search strategies. So let's go to the first solving technique to solve stochastic problems. The idea is to copy every second stage variable and each second stage constraint over the number of scenarios. So here's an illustration of what this would actually mean on search. So we first search on the first stage variables, and then we have a variable and a constraint for each of the scenarios. So we're basically first searching on scenario 1, scenario 2, and so on until scenario n. So this problem is really exploding more or less, because we have all second stage variables and constraints are going to be multiplied by the number of scenarios. And of course, this is also not a very good search strategy, or not a very good strategy, because let's say if the assignment here on scenario 1 is failing, we will still going to search all the way down to scenario n until we will find out about that. So this is, and since the first stage assignment has to hold for each scenario, this is really not a very good approach, but this is the standard approach. So any solver that will do stochastic optimization will provide this solving approach for nonlinear integer problems. So a better approach is, oh, sorry, I'm going to continue with showing you the transformations. So the transformation to this deterministic equivalent does the following. So it leaves the first stage variables and first stage constraints as they are. It's going to introduce an array for all the second stage costs, and it's going to substitute, it's going to extend all the variables and constraints by the number of scenarios. So 1 till s is the scenarios. So as I said, the model is going to explode. As an example, here we can see the deterministic equivalent of the stochastic VRP. So the stochastic parameter now ranges over the number of scenarios and the nodes, so the distance matrix. We have the first stage variables that stay the same. We have this array of the objectives of the second stage, and then here the second stage variables are extended by the number of scenarios, as are the constraints. And we want to minimize over the expected cost. Okay, so the second solving approach is policy-based search, which has actually been proposed by Toby Walsh in 2002. And the idea here is to perform a kind of and/or search. So we consider the stochastic parameters as a kind of decision variable. So we will introduce a scenario variable, and again also compute the objective over the weighted average. So here's an illustration of how policy-based search works. So we are again first starting with the first stage variables, and then we assign here to the scenario variable the number of the scenarios. So we solve scenario 1 in a branch and bound factor. So we solve we get the best solution for scenario 1, and then we perform this OR step. So here we search the best solution for scenario 2, again on the same node as here, and so on for all the scenarios. And then we compute the sum over each of the scenarios, which will give us the objective of this first stage assignment of variables. So this means that we first find an assignment of variables for the first stage, and then we have to perform nested branch and bounds for each of the scenarios. And after this, we can continue on the first stage variable. And the good thing about this kind of search is that if scenario 1 fails here, we're going to immediately backtrack to the first stage. So this is a really nice thing compared to the other solving approach. Of course, it's much more difficult to represent. So here's first of all the transformation of the model with policy-based search. So again, the first stage variables and constraints stay the same. And here we have a variable for the scenarios now. So this is different compared to the other model. And we represent the parameter by an element constraint over the scenario variable. So this is our way on how we can actually do the and/or search, by setting the scenario value in each of those stages. And here's the most interesting part. So here we specify this and/or search, this two-stage search. So let's have a look at this combinator. it's very complex. So let's start with the first part. The first combinator is this nested branch and bound combinator that we use on each of those subtrees, on the recourse trees. So what we're given here is, okay, how to best explain. So what we're doing is, first of all, we're posting that the scenario gets the value I, so the current scenario that we're looking at, and O is the current objective. So this is the branch and bound constraint that we're posting, and then we're performing AND search. So we're searching on the second stage and assign the current best value to O, and then we prune. So this is very similar to this branch and bound combinator that I've showed you before, but just this time we're at the beginning posting the scenario variable and collecting the objective in this position of the array. And the actually policy-based search combinator that we call in the main model now is giving this variable EO, which is the expected objective. So this is the overall objective, and the array of objectives of each scenario. And here again, we apply branch and bound. And what we do here is that we introduce an array of search variables that we initialize with infinity. And we first start, so this is really the definition of this AND OR search. So we first start with the search stage 1, as we saw in the picture, and then we perform portfolio, the portfolio combinator. And the portfolio combinator performs search. So the portfolio combinator gets an array of searches as an argument, and it performs the search of each combinator until one of the combinators is not exhaustive. So as soon as one of them stops, it will track back. So this is what we want, this kind of behavior, as I said before. If the scenario 1 fails, we want to backtrack immediately. Yeah, so this is the policy-based search combinator. Let's have a look at the policy-based search for the stochastic VRP. So, as I said before, we have this variable now for the scenarios. The distance matrix is now initialized, is now indexed by the scenario variable. And down here we specify the two-stage search combinator for search. So now the final and last solving approach for nonlinear integer stochastic optimization problems is called progressive hedging. The idea behind progressive hedging is completely different than the other approaches. The idea is to solve each problem for each scenario in isolation. And since we want to have, since in each of these iterations, we're going to have different first stage assignments, but we want to have the same first stage assignments for all of them, we're trying to, we're going to have an iterative loop where we adapt, where we try to get the first stage variables as close as possible to each other by adapting the objective. So in a way, we're going to relax the problem in each step a bit more to get the same first stage assignments. So again, here we're going to see an illustration of it. So we solve each problem in isolation, and after we solve each of these problems, these assignments here are going to be different. So what we're going to do is we're going to collect all the objectives, and from this we're going to compute a new objective and insert a new objective in each of the problems and resolve again until the gap or the distance between the assignments are equal to a fraction, an epsilon, basically. So this is an approximation approach, and yeah, probably also quite difficult because we are solving an optimization problem in each of those cases, but then again we can solve them in parallel because they're independent. So for progressive hedging, we have a similar transformation then to policy-based search because we also have a variable for each scenario that we basically just set for each of the iterations, for each of the isolations, the isolated solvings. We have a weight that is important that we need for the objective, which will determine how much the objective is going to impact on on the first stage variables. We have here a variable that is also important to update the objective variable. And finally, we have this progressive hedging search combinator. So the progressive hedging search combinator uses the restart primitive. So the restart primitive says that restart as long as the distance, so the distance between the first stage variables, is greater than epsilon. So as long as this condition holds, do the following. So what it does is that it posts again that scenario equals I in an OR search. So this OR search basically really just says perform these searches in parallel, more or less. So we post the scenario equals I, then the branch and bound constraint, and again we first search on the first stage and the second stage. So we really search on the full problem as shown in the image before. And after we've done that, we update the weights, which means that we are updating the weights in the objective, and then we have this iterative loop again. Okay, so this is how progressive hedging would look like for the stochastic VRP. So again, we have a scenario variable, we have the hedging weights, we have this objective for hedging. So this is the actual objective that our objective is to minimize this arrival times, but we have this additional hedging factor as well. So this hedging factor is added in each iteration and is adapted according to the first stage assignments in the other scenarios. And then we define that we want to solve the problem using the progressive hedging search combinator. Okay, so you've seen that we have extended MiniZinc to stochastic MiniZinc, and you've seen that we can transform each of those and the stochastic specification into different solving approaches. Stochastic MiniZinc is a conservative extension of MiniZinc, and as you've also seen, it's agnostic of its solving approach. We can specify the transformations only with the use of search combinators, because the search, as you've seen, is very complex. And at the moment, we know how to specify the search combinators for those three approaches, and the implementation will be released in September. However, the downside of the search combinators is that they're very complex, and it's difficult to actually implement the support in a solver. Because as you've seen, you just simply have to implement all the primitives, but you have to also give the solver also has to allow for the composition of those search combinators. So it's very complex to support, and this is why at the moment we're looking at developing kind of lightweight search combinators that are very easy to support from a solver, and this would make it easier to have solvers supporting the solving approaches for stochastic optimization. Okay, that's it. Thank you. Are there any questions?
I have a question. I have a question in Newcastle.
Yes?
Yeah, back when you're formulating your model, what happens if I have parameters that appear both in the first and second stage?
How would that look like?
Well, I mean, I can just imagine data that I need to read in and use in the model that appears both in first stage and second stage, in terms of calculating coefficients or formulating constraints.
I mean, it's quite easy to determine the stage of a constraint, because as soon as you have a second stage parameter or a second stage variable in that constraint, it's considered a second stage constraint.
Yeah,
Does that answer the question?
I understand that, but my question is if I have a parameter that I'm reading in, my understanding was that if I do not label it with a stage, it's assumed to be stage 1, and if I do label it with a stage, then it gets assigned to that particular stage. And my question is, what if my parameter occurs in both stage 1 and stage 2?
Well, you specify your parameter, I mean, you define your parameter only once in the model. So whatever you assign it to, it will belong to.
The
short answer is stage 1 variables can appear in stage 2 constraints.
Oh, okay. All right. And then my other question is that so I formulate my model, and then can I, rather than using one of your search combinators, can I just say give it to a mixed integer programming solver?
Well, the important thing is that, so for the deterministic equivalent, yes, that's definitely possible, but for the policy-based search and for the progressive hedging approach, the search is key to the solving approach. So just the model itself without the search specification doesn't really mean anything.
So true. For example, if I were to formulate the stochastic model as a deterministic equivalent and then give it to a mixed integer programming solver, then I can choose branching priorities and things like that, which dictate in part dictate my search strategy. But I mean, is that possible?
Yes, that's possible.
Okay. So they were my questions. Thank you.
Are there any more questions?
Yeah, I have a question.
Yes.
The annotations on the stage variables, can you infer them somehow from what data is provided?
Can you infer them from? I didn't understand the last part.
If you know from how the data is specified that it's a stage 2, for example, because you'll provide one for each scenario, right?
Can you hear what he?
He's saying if we looked at the stochastic data file, could we determine the stage 2 parameters just by looking, because those are the ones that occur in the stochastic data file.
Yeah, we should be able to do that, yeah.
Yeah, it's a bit hard for the variables.
Not for the variables, but for the parameters, yes.
Why not the variables?
Because the variables are saying, when do I have to make this decision? Do I make it before I know this or after? And that's not clear.
Okay.
So I have a question. Can you hear me?
A bit, yeah. Can you put the volume up a bit?
Maybe not.
It's not that microphone.
It's not that microphone.
Oh,
yeah, it works now.
yeah, we can hear you now.
Is it this microphone?
Just ask. We can hear you.
You can't define neat stages. So for instance, in your transport problem, even on the morning of departure, I don't know what the traffic conditions are. I only discover the traffic conditions as I'm driving. So I want to optimize over the different possible realizations.
So either you mean, can we do multi-stage, or do you mean some kind of...
So we cannot do online optimization if that's what you want, and we can do multi-stage as well, so that you would say after each time step, the traffic might look in a different way. Yeah.
I guess the trouble is that it's not multi-stage, it's that the stages depend on the solution. So if I go to visit one, or to visit the customer A first, the world is different than if I go to customer B first.
Do you mean that you affect the traffic yourself?
It's just I can't divide up into stages a priori. I have a stage at
Yes, so I guess the VRP model that we've shown here might be a bit artificial in that sense, because what you would do in VRP usually is that you would do online stochastic optimization, where you really have a heuristic on where you are at the moment, where would you actually go, and what is the current situation.
I might ask the question again when I don't have to yell. I'll try later.
Okay.
Do you have any plans to extend this to Markov decision processes, which might actually do more than address field setting?
Did you say Markov decision processing? Yeah. So the difference is that in Markov decision processing, the choice that you make from one node to the other node is, you don't know what you did actually before. In stochastic optimization, this is really the big difference.
Yeah, my question was, do you plan to address them as well in a future version of Zinc, or it's really not?
I don't know. Do we, Peter?
We'd like to. We've got nested constraint programs which allow you to actually directly specify Markov decision processes. So it's certainly now a list of things to get better at solving. But it's hard enough to solve stochastic combinatorial optimization, just even two-stage. So we've got a lot of work. If you're taking arbitrary models, I think that's the key thing. That's where it's difficult for us.
Are there any more questions?
So, Andrea, just a quick question. Are the search combinators that you kind of detailed, are those going to be available for the Mini Zinc solvers that you guys already have? So you can kind of do this end-to-end as long as you stay within sort of the Mini Zinc ecosystem? And the trouble is that other solvers aren't able to understand the complexity of the search combinators? Did I understand the end correctly?
Well, the problem is with the search combinators that I think I just direct this question to Guido. He can answer it best.
Well, currently there's exactly one solver that supports search combinators, so that's a big limitation. And what we're trying to do with this new version, with this light version of Combinators, is that other solvers, or most other solvers that understand Mini Zinc or understand Flat Zinc, should be able to use those search combinators as well. So it's still restricted to Mini Zinc, but I mean we're using Mini Zinc as the input language, so I think that's okay. But the goal is that all solvers that support Mini Zinc can also support these combinators and then support stochastic extensions.
Okay.
The idea of the lightweight search combinators is that all of the search combinator stuff is done in Mini Zinc, except some very limited things, basically that the solver has to be able to run the search for a limited amount of time, or something like that. But it doesn't actually, or it has to be able to, well, that's all really. It's the only real thing that the solver has to be able to do. Return what it finds given this amount of time. And then Mini Zinc will control the search from outside and just repeatedly call the solver.
Okay. Thanks.
Okay, are there any more questions?
All right. Thanks again, Andrea, for giving a great talk.
Thanks.
And then we'll be back for seminar in 2 weeks, and Harris will be talking about cutting cakes. So, see you guys then.